Hey guys, this is Mrs. Harbin, and this is section 1.7 of Algebra 1. Today we are going to take a look at exponents. Just a quick reminder of our biblical integration. The ways of God and His creation are not naturally understood by men, but He gives us tools to examine them in an orderly and organized way. And I hope that you see as we're going throughout math this year that it is orderly, it is organized, that there are patterns and rules that don't just happen accidentally, and that by understanding these patterns and rules, we can better understand the world in an orderly and organized way. So I hope you see that this year. Our objective for today is this. You, the student, will do a couple of different things. First, define terms associated with exponents. Second, simplify and evaluate expressions with integral exponents using the properties of exponents. So, if you didn't pick up on the hint there, we are working with exponents. As a reminder, an exponent is this small little number that tells us how many times to multiply the base. The big number is the base. The small number, the exponent, is how many times we're going to multiply it. So 6 to the third is the same as 6 times 6 times 6. That is an exponential expression. We can read that as 6 to the third power or 6 cubed. The reason we call it 6 cubed is because when we're finding the area or the volume of a cube, we multiply three numbers. All three sides are the same thing in a cube, and we multiply them 3 times, just like 6 times 6 times 6. 5 to the second power is the same as 5 times 5. Notice it is not 5 times 2. It's not 5 groups of 2, but it's 5 groups of 5. And if we kept going, it would be groups of 5, groups of 5, groups of 5. That can be read as 5 to the second power or 5 squared, and that squared terminology comes from the actual square. Don't forget that the squares, perfect squares, and perfect cubes are up on my wall, and we show you the numbers that we know are perfect squares and perfect cubes. Let's take a look at this example. Let's write this with exponents. First, we need to know the base. Well, if we look at what's being multiplied, we see that all of these are 2, so our base is 2. And our exponent is how many times we're multiplying by 2. And that is 1, 2, 3, 4, 5, 6, 7. So 2 times 2 times 2 times 2 times 2 times 2 times 2 is the same thing as 2 to the 7th power. Try this one on your own. How would we write that? If you said negative 3 to the 4th power, correct. Please notice that that negative 3 is in parentheses, and we're going to talk about that in just a second. An important distinction is this. Without those parentheses, you have a negative 3 to the 4th, which means we're taking 3 to the 4th and multiplying it by that negative at the end, making our answer negative. But with parentheses, we have a negative 3 to the 4th power. And that's negative 3 times negative 3 times negative 3 times negative 3, which gives us a positive 81. So those parentheses are important. They tell us whether this negative sign here is part of the exponential expression or whether it's separate and needs to be added at the end. So be careful of those parentheses. Let's evaluate the following expressions. Evaluate is just a fancy word for solve. Simplify it down to one number. And 9 to the 3rd power, we know that's the same as 9 times 9 times 9. And hopefully when you do that on your own, you get 729. Try this one on your own. Negative 7 to the 4th power. Pause if you need to. And after unpausing, you should have gotten 2,401. Try this one on your own. Negative 4 squared, not in parentheses. So that's a negative 4 squared. 4 squared is just 4 times 4. Stick the negative on the end. Nice job if you got negative 16. Now, exponents do have some properties that help us to combine and simplify them. Let's take a look not here, but at the actual definitions. Let me skip ahead a little bit. So our first property of exponents is the product property, which means that when we multiply like bases, we can just add the exponents. Let's take a look at what that looks like without any numbers. Without numbers, we have like bases. Both of our bases are x. We're multiplying these bases. And what we can do as a little shortcut is take our two exponents and add them together. Let's put some numbers with this, shall we? I'm going to back up a little bit here. So with numbers, we've got 5 to the second times 5 to the third. Our bases are the same and we're multiplying them. So we can just combine the bases. 5 to the second times 5 to the third is the same as 5 to the second plus 5 to the third. 5 to the second plus third, which is 5 to the fifth. If we write that out, here's how we get to that. 5 to the second is 5 times 5. 5 to the third is 5 times 5 times 5. We can do a quick count. 1, 2, 3, 4, 5. And see that we're multiplying 5 times itself 5 times, which is what we just said right up here with our product property of exponents. All right, our second rule of exponents is called the quotient property. And in the quotient property, if we are dividing like bases, we subtract the exponents. This is what it looks like without numbers. X to the a divided by x to the b equals x minus a to the b. Or what if we had x to the fifth divided by x to the third? If I write that out, it looks like this. 8 times 8, I said x earlier, I meant 8. 8 times 8 times 8 times 8 times 8, there's 8 to the fifth, divided by 8 to the third. 8 times 8 times 8. We know that in fractions or in division, things can cancel each other out. So this 8 over this 8, they cancel. They're just equal to 1. And this 8 divided by this 8 is equal to 1. And this 8 divided by this 8 is equal to 1. That leaves us 8 squared. A shortcut would have been to take that and write it this way. Common base, 8. Subtract our two exponents, 5 minus 3. And that gives us 8 to the second power. Now, if you wanted to, you could write out your 8s every time like I did, but some of these are going to get pretty long, so your quotient rule is going to save you some time. Another property of exponents is the power property. That's when we're raising a power to another power. We're doing exponents twice. In that case, we can multiply the exponents. So we're raising a base to a power and raising that whole thing to another power. We can just take our two exponents and multiply them, keeping the base the same. Here's what it looks like with numbers. 2 to the third power, and all of that raised again to the second power. That's the same as 2 to the 3 times 2. Which is 2 to the 6. To show you that this is in fact true, 2 to the third power is 2 times 2 times 2. Yep, that's 8. Raised to the second power. And 8 to the second power is 8 times 8, 64. If we come over here and we do 2 to the 6th power, 2 times 2 times 2 times 2 times 2 times 2. You can do that on your calculator if you want to verify that it's also 64. But I'll tell you 2 times 2 is 4. Times 2 is 8. Times 2 is 16. Times 2 is 32. And times that last 2 is indeed 64. So this way, option 1 over here was much faster than this way. We can use that product power property of exponents as a shortcut to find these answers. Let's try some examples on your own. I want you to simplify these, but leave them in exponential form. What's another way we could write 5 to the second times 5 to the 10th? If you said, Mrs. Harbin, they have like bases, and we can use the product property of exponents, and all we have to do is add the exponents to get 5 to the 12th, then you're a genius and you can skip the rest of this video. Or not. But you are correct. Product property of exponents. What about 3 to the second times 3 to the 4th times 3 to the 9th? Yep, like bases, different exponents. Let's use the product property of exponents to add those exponents, which gives us 3 to the 15th. Our base stays the same. 2 to the 4th divided by 2. Well, 2 by itself is just 2 to the first power, in case you're wondering where that exponent is. We can subtract our exponents, giving us 2 to the third. Remember, if we write this out, this looks like 2 times 2 times 2 times 2, that's 2 to the fourth, over 2, 2 to the first power. These cancel out, which leaves us 2 times 2 times 2, 2 to the third power, which is what we just proved. All right, what about this one? 10 to the fifth divided by 10 to the third. Try that on your own. If you recognize, use the quotient rule of exponents and get 10 to the fifth minus 10 to the third. 10 to the fifth minus third, then that gives you 10 to the second. Nice job. 5 to the third raised to the sixth power. Yep, we're going to take that 5 and keep our base the same and multiply the 3 times the 6, which gets us 5 to the 18th. Nice job. The quotient property allows us to also give meaning to negative exponents. If you have x to the second over x to the third, 2 minus 3 is negative 1. That's the same thing as x to the negative 1. We have more x's in the denominator than we do in the numerator of this fraction. A way that we can write that in a positive way is 1 over x to the first power. We can take this x to the negative 1, and when we write it in its reciprocal form, that x becomes positive. Any non-zero number to the 0 power equals 1. Anything raised to the 0 power equals 1. Any non-zero number. So we can't raise 0 to the 0 power, but every other number to the 0 power is 1. Now let's take a look again at some negative exponents. We said that when an exponent is negative, we can just write the reciprocal, stick that exponent on the bottom, and it's no longer negative. Well, the converse is true. If we have a negative in the bottom, all we have to do is write the inverse of that. So if it's 1 over x to the negative a, to make it positive, we just have x to the a over 1. We flip that fraction around. Now we don't write the over 1 part, but it's implied. I wanted to write that there so you could see all we're doing is just flipping that fraction around, inverting it. Okay, try these examples. Evaluate negative 2 to the fourth power. Now it's got parentheses around it, so think about what that means. Nice job if you got 1 over 16. 1 over 16, that negative exponent moved us into the bottom of a fraction, which is where that 1 over 16 came from. Negative 3 to the negative 2 power. Notice that the negative 3 is not in parentheses, so this is negative 3 to the negative 2 power. We rewrite that as negative 1 over 3 to the second power, or 3 squared, and that becomes 1 over 9. That negative sign stays out here because it was not part of the original expression there. Try this one on your own. How could we rewrite that without a negative exponent? If you said use the inverse and wrote 6 to the third, nice job. 6 to the third is 216. Excellent. Simplify, leaving each answer in positive exponential form. In positive exponential form. So we may have to use some inverted expressions here. 3 to the negative 9th times 3 to the 7th. Try that one on your own. After you've tried it, come back and check your work. That's 3 to the negative 9 plus 7, which is 3 to the negative 2. In order to get that positive, we've got to invert it, which becomes 1 over 3 squared. If we simplify that even further, it would become 1 over 9, but it did tell us to leave it in exponential form, so we're going to stop right there. 2 to the negative 3 times 2 to the negative 2 is 2 to the negative 3 minus negative 2, 2 to the 5th. Negative 5th, we've got to invert that to make it positive, 1 over 2 to the 5th. Nice job. Simplify and leave each answer in positive exponential form. 4 to the negative 2 divided by 4 to the negative 3. That's 4 to the negative 2 minus negative 3. And the opposite of negative 3, which leaves us with 4 to the first power, which can be just written as 4. Try this one. 5 to the negative 3 to the fourth power.